Welcome to a lesson with Dr. Powell. Let's look at a proof of the law of quadratic reciprocity. It states that Q being a square mod P is equivalent to P star being a square mod Q, where P star is equal to positive P when P is congruent to 1 mod 4, so that P minus 1 would be a multiple of 4, and hence this exponent right here would be even. And it's equal to precisely negative P when P is congruent to 3 mod 4, so that this exponent would be odd. Okay, so here's the setup. Let's take zeta as a pth root of unity in the complex numbers. Now, if we were to compute the discriminant of the powers of zeta, remember that it is a square of a Vandermonde determinant, and the Vandermonde determinant lives in this field Q adjoins zeta, so that the square root of whatever we get, which is the Vandermonde determinant, will live in here. Okay, so when we compute the discriminant, it has a nice form. It's a power of P times this power of -1, and we know its square root lives in this field. And notice that this power right here is odd, and so we can divide out by a square integer and get this, which will still be a square, and that's P star. So we know that P star has a square root in this particular field. Now consider the Galois group of Q adjoins zeta over Q. So automorphisms are uniquely determined by a power that zeta is sent to. And powers are these exponents. When they multiply, that's like composing two different automorphisms. So the automorphism group is like the multiplicative group of mod P, since the exponents themselves live mod P, with this being a pth root of unity. The order of this multiplicative group is P minus 1, and it's cyclic, meaning that it has unique subgroups of indices that are factors of P minus 1. P minus 1 is even. It has a unique index 2 subgroup. That unique index 2 subgroup corresponds to, via Galois correspondence, to unique fixed field, to its fixed field, which is a unique extension of Q of degree 2. Okay, and it has to be this one, since we just discovered that this is a subfield, a quadratic subfield of this. So the unique index 2 subgroup here will have as its fixed field Q adjoined square root of P star. Now, what we're going to be doing is we're going to be looking at how Q behaves as we lift it to different primes in these different extensions. It's important to realize that Q is unramified. One way of noticing that is looking at another form for the discriminant, another formula for it, which involves the derivative of the minimal polynomial, of where f is the minimal polynomial of zeta, and we know that this is the discriminant, which is a power of P, so it's doesn't have any factors that have Q in it or anything, so it'll be non-zero mod Q. So this is a non-zero mod Q. That means that that the derivative with zeta plugged in will be non-zero mod Q when we're up in OL. So Q times OL, we mod out by that. When we're up here, that'll be non-zero, which tells us something. It tells us through a little bit of thought that if we mod out if we take the minimal polynomial and we mod it out by q and then look and see how it factors, that it's that when we take the then when we take the derivative and plug in a root of f, it will be non-zero, which means that f mod q has no square factors. But if it has no square factors, then q itself will not decompose as a prime multiplied to itself anywhere along the line, which means it's unramified. Its ramification index is 1 the whole way through in each extension. So E will always be equal to 1. What we're going to show now is that F, with the inertial degree, will be also equal to 1, which will force R to be 2, which will make Q actually split right here. Now, the way to do that, though, is we're going to assume that Q is a square mod P. Now, if Q is a square mod P, remember this, an automorphism raising to a power, right here is like thinking about this group right here, this multiplicative group. So where Q is behaving mod P, but multiplicatively. And if Q is a square, that means it lives in the unique index 2 subgroup, or at least the automorphism that described by raising it to a power lives in that unique subgroup. So if you take like a primitive root or like a generator of that multiplicative cyclic group, and you'll get all even powers of it, that's the unique index 2 subgroup. And if Q is a square, that's like saying Q's in that subgroup. Well, if Q's in that unique, so zeta, so this automorphism right here that sends zeta to the Q is in that unique index 2 subgroup, which means that it will fix K. So what we've just shown is Q being a square mod P is the same thing as saying that the automorphism sigma Q fixes K. Okay, let's think about this a little bit between finite fields now to consider inertial degrees. Let's consider OL modded out by a prime that lies over Q. This is a finite field and a vector space over Z mod QZ. It's the degree of this extension is F, and the dimension of this as a vector space is also F. And the number of elements is Q to the F. And this is a finite field, and all non-zero elements are roots of unity, which actually gives us that this particular that all the elements of this field are roots of this polynomial right here. And this polynomial is separable. It has distinct roots. And in particular, if we move x over to the other side, this is kind of like saying x to the q times q, 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 q. It's like doing this automorphism, like something goes to the qth power and then to the qth power again, the qth power again, but you do it f times. So you run this automorphism f times, and here when we raise something to the qth power, that actually is a nice automorphism. It has to do with binomial coefficients and q being multiples of q. And so you get, and anyhow, when you expand two things added together raised to a qth power, so you get a nice automorphism. It's called the Frobenius automorphism. And in particular, it's the order of this Frobenius automorphism is actually f itself. F is the minimal thing that would allow this x going to x to q to be the identity minimally. And in particular because all these roots are distinct, and so f is the smallest thing that you could possibly have here in order to get the identity on all the roots right here. So what we have in particular is that so in the Galois group, this is a Galois extension of this finite field over this one, has degree or has order f. Okay, so suppose it has order f right here, and also realize that where this Frobenius element has, or automorphism, has come from, it's come from raising something to the qth power, which if you take this automorphism and restrict it to OL, and then you look at it in the different mods, it actually restricts down to that Frobenius automorphism. And which tells us a couple of things. It tells us that the Frobenius automorphism actually fixes this field right here, this finite subfield of this guy, which means that that the Galois group of this field over this one actually has order f. But the one over this one to this one also has order f, and f is the degree of the extension. So the degree of the extension from here to here is f, and from here to here is f, which forces the degree of this extension right here to be 1, or trivial, which means that the inertial degree of this the extension from q to the prime q, from q to k, right here, that f has to be 1 in this case, which would force r, which is the number of primes that q splits into in a product, to be exactly 2. Okay, so we know that q splits in its factorization. So if you take the minimal polynomial of p star over q, since q splits, then that means that this polynomial must factor non-trivially mod q. But if it factors non-trivially mod q, that actually forces p star itself to be a square mod q. So what we have just shown is that if q is a square mod p, then p star is a square mod q. And it goes back the other way too. Let's see why. Okay, let's see why. Okay, right here. So p star is a square mod q means that we actually get a factorization mod q. If a factorization mod q means that q splits. If q splits in the degree 2 extension, that forces, and we already know this is 1, but we know that f in that extension is 1, so the inertial degree is 1. If the inertial degree is 1, that means that if the inertial degree is 1, that means that this is trivial, which means that this automorphism actually fixes, this automorphism is actually in the index 2 subgroup, which fixes k. And if it's in that index 2 subgroup, then q is a square mod p. So we have just completed the proof of the law of quadratic reciprocity using a little bit of algebraic number theory. Thank you for watching.